Yeah, Snail, you can start.
Okay, so good afternoon, everyone. Welcome to the first Math Club talk of the fall 2022 semester. For the first years, Math Club is a students club at ISI Bangalore, which organizes several different events and mathematical activities. For example, there are professor lectures, guest lectures, student lectures, and other reading projects, and so on. So the target is to do mathematics beyond the curriculum. We also, one of our target is to promote UG level research and to sort of motivate everybody to do research from a very early stage. So we also accept paper submissions, have some reading groups and student talks as well. So you are welcome to present and be a part of Math Club as well. We'll send a mail soon to you guys about that. But for today, so let's focus on today's talk for now. So today's talk would be presented by Soham Bakshi, a student of B3, the third year of B.Math. His research interests are statistics, probability, and geometrical analysis. Today's topic is geometry on statistical models. Hope you will enjoy the talk. So over to you, Bakshi.
Also, in case of any doubts, you can just unmute yourself and ask the questions to the host.
Yep.
I guess Bakshi is experiencing some technical problems. In just a second.
Yeah, so is it visible?
Yes.
Great.
Yeah, you can start.
Okay. So today topic of this presentation will be geometry on statistical models. So by that, what I mean is doing Riemannian geometric modeling on statistical models. So statistical models can be thought of just a space of probability distributions. Okay, so let's just see what we are going to do. What is the idea? So we are going to find geometric structures in the space or subspaces of probability distributions. For example, let's say we take the space of all normals, normal mu sigma squares. So we want to give some idea of the geometric structures in that space, like how far apart two distributions are. So that's the first perspective to look at it. That's from distance or divergence. So that is asking the simple questions like how far apart two distributions are, or what can be measure of difference between two populations. So when we do statistics, when we take a population, we model the population with some distribution, right? So that's basically asking like what's the measure of difference between two distributions. So another way to look at it or to motivate this kind of study, geometric study on statistical models, is the very nice geometric interpretation of information loss. By this particular modeling, what we can do is we can talk about smallest information transforms. So we'll see that will be basically the geodesic. So we are moving from one distribution to another. We're transforming from one distribution to another by losing the least amount of information we can. So that's basically the idea of the information loss and the way we look at it geometrically. There are several other ways to look at it and several other places and motivations from where we can really derive this way of thinking. But yeah, so another one is statistical curvature. So Fisher-Rao in 1975 with one of his paper, he defined something called a statistical curvature, which measures like how far away you are from the exponential families. So the exponential families are well behaved. We have several kinds of formulas and things for even statistical estimation. We have some special kinds of things which we can say upon exponential families. So now he introduced something, a very geometric notion of statistical curvature, which somehow signifies the departure from exponentiality of a particular distribution. Okay, so this is basically the motivation of looking at the space of probability distributions geometrically. And if you are a mathematician, then of course you don't need all that. Geometry is never boring, so we can just do it. Okay, so let's just start with defining basic notions of Riemannian geometry and differential geometry on manifolds. So I can't really go deep into them and talk the real geometric notions or even the rigorous definitions of them, because defining stuff here in Riemannian geometric notions are difficult. Like you need to even define small things like tangent vectors by defining like differentiating operators and so on. So I will not go into all that, but I will just try to give a basic understanding of what manifolds are and Riemannian metric is. So basically, we'll start with a smooth manifold. So a manifold is basically a locally which are Euclidean spaces. So it will look like something like this. So this is a manifold, and what you can see here and here. So these two things are local homeomorphisms from some subspace of Rm, and yeah, so it's an m-dimensional manifold. Okay, so they will be locally like Euclidean spaces. So they are like many Euclidean spaces glued together. And if the transition of all these local patches are smooth, then we in some sense, then we call the manifolds to be smooth. Okay. Okay. So now this is a very basic concept which we'll see again and again throughout the lecture. That is tangent space. So this is same as what we intuitively think of tangent spaces like. I can't find my pencil. Yeah. Okay. So yeah, so basically it's like, I will try to draw some picture. So it's just like that. Okay. So you can think like the tangent vectors are the possible directions passing tangentially through a point in a manifold. Okay. And so this is a vector space. So a tangent space is a vector space. And what we get is that the basis vectors can be like, the basis vectors are basically the partial derivatives operators. So these are exactly operators, but we're not going to write them like that. But okay, so anyway, just think of it as there is a tangent space which is a vector space, and there are basis vectors, and the basis vectors can be written as the partial derivatives with respect to a particular chart, so particular parameterization. Okay, so these are basically a tangent space. So at each point in a manifold you will get a tangent space. So that is basically the space of all the tangential directions from that point. Great. Yeah, so now we define Riemannian metric, which is the first basic step going to define abstract Riemannian manifold. So what we do basically is we define inner products on each tangent spaces. So at each point in a smooth manifold, we have a tangent space. So now what we do is we define GP. So we define GP, which is a positive definite symmetric bilinear form. Okay, at P, at a particular point P. So this is basically inner product at the tangent space of P. Okay, and the transition from P to GP should also be smooth. So these are like geometric smoothness conditions. So basically we're trying to give like some more information on the tangent spaces at each point. Okay, like inner products, like angles, like lengths, and so on. So now we know what is the length of a tangent vector at a point, right? After defining the Riemannian metric. Okay, so one thing we can note here is to define a Riemannian metric. So what we basically need to do is define a positive definite and symmetric bilinear form on TPM. So TPM is the tangent space at the point P. Okay, so we don't really need to define the inner product for all the vectors. We can just do it for the basis vectors, and that will be sufficient to get the inner product on any other two vectors. Okay, so that is something which we will see later. Okay, so just to note here. So now what are vector fields? Vector fields are just, so what they do basically is they map a point to a particular tangent vector at its own tangent space. Okay. For example, let's say you take the velocity vector. So that actually it's a vector field. So if you have a curve, for example, in a Riemannian manifold, and then you take the derivative of it, so that is this. So this at time t will be, so suppose this is gamma t, then at this point so this will map this point to a tangent vector, right? Tangent vector in this at this point, right? So this will be at something, yeah. So yeah. So these are, so at each point there will be some mappings, right? So that there is a vector map. So these are vector fields. So this gamma dot t is a vector field on the curve gamma. So vector field basically is a mapping from M to the tangent bundle Tm. So tangent bundle is just the union of all the tangent spaces. Okay. So at each point we're mapping the point to a particular tangent vector on its own tangent space. That's all we're doing. And we denote the set of all vector fields by this chi-m or whatever. Yeah. Now we move on to the next most important part. So I think like going so quickly over all this really abstract and difficult notions may be difficult, but okay, I don't really have any other option. So affine connections, what we basically do is there is no point of looking into them and, like, so what we basically are trying to do is we are basically connecting different tangent spaces and trying to form relation between two different tangent spaces. So far we have Riemannian metric, which gives more geometric information on each tangent space of the manifold, right? But we don't really have any global notion of geometry yet. We can't connect to different tangent spaces at different points. So what can we do then? Or another motivation is parallel transport. So we are not discussing parallel transport here, but what we are trying to do is basically from one, so let me try to draw a picture. So from one tangent space, we are trying to move one vector, tangent vector, parallelly along a smooth curve to another tangent space. Okay. So, and likewise, we are defining connections or linear connections on the manifold. Or this definition particularly is defining in the terms of covariant derivative, okay, of a particular vector field along another vector field. Okay. So yeah, so those are the notions of which basically let you talk about geodesics, curvature of statistical manifold or any general manifold and so on, like the global geometric properties. Just with a Riemannian metric, you won't be able to talk about all that, okay? Okay, so after defining affine connections, we can really talk about what's the length of a curve on a Riemannian manifold. We can talk about even a length of a curve even before that, but okay. And also we can talk about geodesics, curvature, and other geometric properties of a manifold. And it's to define an affine connection, sometimes we just, okay, so before that, so there is one compatible and symmetric affine connection associated with every Riemannian metric G. So that is a fundamental theorem of Riemannian geometry, which says that if you start with a Riemannian manifold, that is a manifold M and a Riemannian metric G on it, then there exists a unique linear connection nabla on M that is compatible with G and symmetric. So yeah, so symmetric is also sometimes called torsion free. Okay. So what we mean by symmetry, so the thing is, to be symmetric, we need to satisfy this. There is nabla of is equal to.
Yeah, so this linear connection allows me to basically differentiate by approaching it by any point. So basically some kind of differential, some kind of directional derivative, right?
Exactly. So differentiate along a vector field. So you're differentiating one vector field with respect to another vector field. So that's the idea. Yeah.
Yeah, I see. Got it.
Yeah. So it can be actually better motivated by looking at the parallel translations. But yeah, so those are really very nice geometric interpretations of these things. But we don't really have time to talk about all that. But anyway, so this is the notion of symmetric, okay, or torsion free. And we'll see later that these connections can also be, defined in terms of Christoffel symbols, okay, of first kind and second kind. So those are, the local information of these connections are expressed through the Christoffel symbols. And in terms of Christoffel symbol, also the symmetricity can be written as, I think this, yeah. So ijk is equal to jik. So yeah, so then we call the connection symmetric on a particular metric G. Okay. And yeah, and it's compatible if this thing happens. And these are really like nice geometric things which we can't really see because we are just getting familiarized with so many things at the same time. Okay. But anyway, so this is saying just that given a Riemannian metric, we can always get a unique connection, which is sometimes called the Levi-Civita connection or the Riemannian connection, which is compatible with that Riemannian metric and also symmetric with respect to it. Okay. And the fundamental Riemannian geometry or the Riemannian geometry mathematicians do is were like always based on this Levi-Civita connection. So when they talk about a Riemannian manifold, they include the Levi-Civita connection on it. Okay. But we'll see while studying statistical or information manifolds, we don't really are so much biased towards, symmetric connections. We can go here and there and look at different connections and do. So yeah, so we'll look at all that. Let's just move forward. Okay. Yeah, so this is also called the Levi-Civita connection with respect to G. And as I said that sometimes we locally define these connections by using the Christoffel symbols of first kind and second kind. Okay, and which are defined by these equations. Okay, so if you're given these Christoffel symbols, we can find out this nabla, the connection by this and also. Okay, and one more thing here, this is a use of Einstein summation convention or something, it's called like that. And what we're basically doing is we are removing the summation notation. So here you can see there is a summation notation. Yeah, but here there is not. But essentially there should be a summation notation here. But we'll skip all these notations like this symbols of sum in many cases, and this is called the some Einstein summation convention. So we are going to use it. Okay. Okay, so what these local Christoffel symbols basically show is like at least of the first kind. So of the second kind. So the first kind is defined from the second kind and the Riemannian metric G in terms of both of that. And the Christoffel symbol of the second kind is actually, it shows that how the tangent vectors changes on a manifold. Okay. So, and how a tangent vector will change depends on what basis you have chosen in that particular tangent space, right? Yeah, so what basis you have in tangent space essentially depends on what parametrization or what is your local chart, what is your local homeomorphism. Okay. Yeah. Okay, so now there is a very important geometric notion on statistical manifolds or manifolds too. That is flatness. So when do we call a manifold or Riemannian manifold to be flat? We call it if we have an affine coordinate system for the connection. Okay, so what is that? So one thing, these Christoffel symbols, we go back to the last slide. So these Christoffel symbols are dependent on the parametrization. Okay, dependent on the coordinate systems we take, but the connection shouldn't be. So that is the thing, we are doing local things, so locally it will be, but yeah, in all it's not. And then suppose, so when we call it to be flat, when there is an affine coordinate system for the connection nabla. Okay, that is a set of n basis vector fields. So okay, we'll use both of these notations. So it's best to be comfortable with both of them. So we'll sometimes write the basis vector as ei, and sometimes we can also write it as partial I, because it can be treated as the partial operators, okay, with respect to the parameterization. And when they're parallelness, like all the basis vector fields are parallel, then we call that this is flat with respect to the connection nabla. Okay, so manifold is flat with respect to a connection nabla if there exists an affine coordinate system for the connection nabla. So we need to find a coordinate system for the connection nabla in which all the Christoffel symbols are 0 of second kind. Okay, so these are like equivalent conditions for existence of an affine coordinate system. Okay, so basically the tangent vectors are all like, they're not at all changing along the manifolds. That's why we're calling them flat. Okay, but another thing to note here is flatness of a manifold depends on the connection. It's not a complete geometric property of the manifold. It depends on what connection we're working with. Okay. And in generally in Riemannian geometry, work with the Levi-Civita connection, which is a compatible and symmetric connection with respect to the Riemannian metric G. But in our case, we won't be. Okay. And now the most important thing, which is the shortest, shortest distance curves in some sense. So those are called the geodesic. So the definition of geodesics are not at all like that. Definition is very simple. It's saying the acceleration of the curve should be 0. So to define acceleration of a curve, you need to define the velocity vector field on the curve and then differentiate the velocity vector field with respect to that curve and then get the acceleration. And then if the acceleration is 0, then you say that the curve is a geodesic. Okay. Okay. So you are basically trying to, like, this is some analogy from straight lines on. So we'll see examples. So exactly. So straight lines on with constant parametrization on Euclidean spaces. So basically, for a curve to be a geodesic, what we need to have is all the tangent vectors should be parallel. Like, yeah. So actually, there are autoparallel submanifolds. So this is a generalization of geodesics. So geodesic are just a one-dimensional autoparallel submanifolds. So basically, autoparallel submanifolds. Okay, so I will not define all that, but let's just draw a picture and see. So something like that. So suppose, yeah, so if we take the tangent vectors here, so you'll see everything is like that. Okay. But when we are taking in this direction, it is like this, and so they're not parallel. So this is a geodesic and this is not. When you will look at sphere, then it will be the big diametric circles. Anyway, so these are the geodesic curves. And then we have a notion of curve length defined very similarly on Riemannian manifolds. We just take norm of the derivative of the curve. Okay. And then how do we take the norm? So this is basically a tangent, this thing of tangent vectors, right? So now taking norm means we are going into the space of tangent space. And there we already have an inner product defined. What is inner product? That's the Riemannian metric G. So it's basically this. Okay. And again, we are missing a summation here. We are not missing it. It's again some convention. So we're not using the summations. So nothing to get afraid of that. Okay. So I think this is also clear. So we are just writing this as this. Okay. The summation, we are skipping the summation, writing this in the matrix form of Gij. So yeah, so this is what I wanted to note there, that to define a metric, a Riemannian metric, it's just sufficient to define a G as matrix, which is just the Gij, just the Gij matrix. Where Gij is G on the I and jth basis vectors on the tangent space. Okay. And so this is how we define a Riemannian distance, curve length on a Riemannian manifold. So this is the curve and joining A and B, 2 points on a Riemannian manifold. And this is the distance, this is the length of the curve. And now, so what is the Riemannian distance? It is the infimum of all the lengths of all possible curves joining P and P to Q. So dPQ is just the infimum over all the possible admissible curves. So not all curves, smooth curves and all. So those are called admissible curves. So I'm not going into all those details. From P to Q, you need to see what is the smallest length curve possible joining P and Q. So that's the length minimizing curve, and the length of that is the distance. Okay. And there may not always exist a length minimizing curve, but the distance is always defined if it's path connected and so on. But okay, again, we will not go into all that. So now there are two very important results to connect the notion of geodesics with length minimizing curves and Riemannian distance. The first says that every minimizing curve on a Riemannian manifold is basically a geodesic with a unit speed parameterization. Okay. And the second one says that every Riemannian geodesic is locally minimizing. Okay. So basically, at least in our case, when we're doing statistics and statistical manifold applying Riemannian geometry, you don't need to be very specific about finding or minimizing curves and all. We can just, in most cases, just find out the geodesic. So how to find out the geodesic? That's also a question. So we define geodesic by saying that the acceleration should be 0. So if you calculate the expression of acceleration, it will come in terms of the Christoffel symbols and the Riemannian metric G, and it will be some, differential equation, and you can solve it, and there are theorems for its uniqueness, uniqueness of the solution, and so on, and you will get a geodesic. So in most cases, when we are modeling Riemannian geometry, what we basically do is to find the distance between 2 points. We try to find the geodesic, which is going from that point to the other point. And then we integrate along that geodesic to find the curve length. And that's the distance between 2 points in a Riemannian manifold. Okay. I hope it's at least little bit clear and comfortable with all. Okay. So, so these are the basic notions of Riemannian geometry. So to sum up, to model something in Riemannian geometric sense, what we need to do is start with a smooth manifold and then define Riemannian metric GP. So GP, at each point, you are defining a inner product, symmetric, positive definite bilinear form on the tangent space at P. Okay. Or equivalently, you can define, as I said, the metric for the on the basis vectors. So just define a we have to find some matrix G of elements Gij, where Gij is just this. Okay. So this is Gij. So basically, to start modeling, we need to get some good function, this Gij, some good function of P. Like we need to replace this G matrix with something else which satisfies the properties, right? And then what we can do is we can define affine connections or specify Cristobal symbols locally. And to do that, do we only have Levi-Civita, that is a compatible symmetric? No. And that's the interesting part. We'll see that. So basically, after defining Riemannian metric, we'll look at various connections. And the connections are essentially defined in terms of the G, the Riemannian metric G, because it's respect to that metric. And after defining the connection, you can talk about is a manifold flat with respect to this connection or not? What are the geodesics? What are the lengths and so on? What is the curvature and so on? Okay, so that's all about Riemannian geometry and what we need to model our, geometric modeling of parametric models. So now let's move on to parametric models and see what they are. So as I said, they are space of their family of probability density functions. Okay, so and they're parametric in nature. That is, you need to determine the distribution given a set of parameters. Let's say n dimensions of parameters. Okay, and then we call this to be the parametric space, theta a subset of Rn, and we will impose some conditions on how the parametric space can be, how the parameterizations are. Those are the regularity conditions. But basically, it will be a parametric statistical model, which is just a family of probability density functions uniquely determined by the parameters. Okay. And as you can see, all these probability distribution functions are L1 functions, right? So you can just think S as a subset of the infinite dimensional space of L1 functions. So it's already, it already has an embedded geometry. And now we'll impose certain regularity conditions to do geometry in a better way. Firstly is the parameter space should be homeomorphic to an open subset of Rn. Okay. That's something we need because we are, as we know, we are going to model this statistical model as a manifold first. We'll start with modeling it as a smooth manifold. So we need a homeomorphism from a open subset of Rn. Okay. So that is in this case the parameter space. And these parameterizations are basically the charts. Okay, basically the the coordinates. Okay. And the topology of S induced from Rn is compatible with the subspace topology of S in L1 space. That's also important. Then again, we should have constant support. So Px theta, the support of Px theta should not depend on theta. So that should be the case, right? So for example, just think whenever we're thinking of statistical models, you can just take an example of Gaussians, like normals or whatever else, any parametric distribution, even multivariate normals, those are also parametric, right? So yeah. So yeah, so you can, yeah. So basically we're trying to say that the normal mu sigma square, so the support of them is constant, whatever the mu and sigma square are, right? So that is one assumption on this statistical models we need. And then we need this partial derivatives with respect to these theta i's to be linearly independent. So again, so these will be vectors. These can be thought of as tangent vectors. So now, so let us just see how we can look at a statistical model. Okay, so suppose here there is a mu sigma square, mu 1 sigma 1 square, and there is a mu 2 sigma 2 square. Okay. And so from here, there can be two directions. So here is a two-dimensional statistical model. So there can be two directions, one in the direction of mu and the other in the direction of sigma or sigma square. So that is, so we'll write this as d mu and d sigma. Sorry, partial mu and partial sigma. Yeah. One can also think of there are good distributions like trinomial distribution, and then the space is just a simplex on R2, right? And then you can actually transform that into a sphere, and then you can talk about lengths in that, and those are like really very connected geometrically. So okay, so anyway, so we are basically like these partials with respect to a particular, the theta i's are just signifying directions on the tangent space at a point P, right? From our smooth manifold modeling. Okay. And with this fold, we also need some smoothness and exchangeability conditions on the partial differentiations and the integrations also to define Fisher information and so on later. But we need, so okay, so there are certain geometric, like certain regularity conditions we need to assume and then go on doing all these things. But the models we see, like the distributions we work with, generally satisfy all these conditions. Okay, so this is a very important thing, a very important function called score functions. So first, okay, so log likelihood function, I think everybody knows this, but this is just taking the log likelihood of the p theta. Okay, so this can be thought of like this is a function from S to set of all functions from the sample space to R. Okay, and now we are not really interested about X. Okay, so we start with fixing a data or like some data X is there. Okay, but this is like all the points will be parameterized by the thetas, right? So we sometimes write the likelihood function as Lx theta, which is just LPx, like the same thing, just we write it differently. Okay, and then we differentiate this log likelihood function with respect to different theta i's, right? We have theta 1 to theta n parameter. Yeah, so these are called the score functions. So what they signify is how the information contained in p theta changes in the direction of theta j. Okay, so basically differentiating Lx theta, which is a function of the whole vector theta, with partially differentiating it with respect to theta j. So you're moving along theta j, and you're looking at how does the likelihood function changes. Okay, so how much information about that particular theta is contained in the data X, that is the likelihood function, right? And then we differentiate it with respect in a particular direction, theta j. So it's signifying the information contained in p theta which changes in the direction of theta j. Okay. And these functions will play a very crucial role in defining Fisher information matrix and so on. We'll see that. So what is a Fisher information matrix? So why we are doing all that? We are just trying to be familiarized with basic parametric models and what we can do in them. And after that, we'll see like parametric model and take something from there to define the Riemannian metric and go so on doing Riemannian geometry on it. Okay, so this will be a very key factor defining the Riemannian metric. Basically, this will be the coefficients of the Riemannian matrix. This is the information matrix, which is also known as the Fisher information matrix. So for one parameter case, there are Fisher information numbers, which like I should have mentioned them to give a bit more motivation, but yeah. So this matrix is defined, the ij term is defined with this expression, taking the expectation of partial I with respect to the theta I and then partial j. Okay. So in the diagonals is just the information number only for the theta i's. Okay. And this can also be written as this. We are just the expectation we are breaking down in the integrals. And then if we differentiate it and then take some computations, yeah. So if we just differentiate it, and then I think there will be 1 by p theta x, and that will be cancelled out because there is another 1 p theta x here. So yeah, so there will be 1 remaining, and okay. So this will be, finally you will get this. Okay. So these are few equivalent ways to write the ijth element of the information matrix. So basically information matrix, what you are looking at are like how the information is changing going into directions. So this particular quantity, you have two like partial I, partial j, so it's not basically going into a particular direction, but yeah, so some idea like that. So something like how the information changes going here and there along the manifold or along the different directions. Okay, so some information around that is stored in this Fisher information matrix. And we'll use that to define the Riemannian metric. Okay. So there is a very important result here, which says that the Fisher information matrix on any geometrically regular statistical model is symmetric and positive definite. Actually, it's always symmetric and positive semi-definite, but if we impose this linearity of these partials, these basis vectors, then we get positive definite also. And this is a proof of it. It's pretty easy, I think. You just take a vector and just do the thing. So the thing is, you can just, these are the assumptions. We can redistribute and we can take the integral out and summation inside, and then, yeah, so this will be just a square greater than or equal to 0, and it will be equal to 0 if and only if the summation of bi partial theta I square root of p is equal to 0. And that will happen if and only if, and because from the independence of partial theta I p, that can happen if and only if we have all the vectors 0, vi equal to 0. So that is, this is strictly greater than 0 if not v is equal to 0. So this is positive definite. Ij are positive. So the Fisher information matrix is a symmetric positive definite. Symmetric is very clear from the formula, right? We define the ij element expectation of partial I of the likelihood and partial j of the likelihood. So you can just exchange it and same. Okay, so this is a very crucial result, because if we remember, then in the definition of Riemannian metric, we also had symmetric and positive definite bilinear form. And also we saw that defining a particular kind of matrix G, where all the ijth element is just the G, like Riemannian metric over the inner product on the ith and jth basis, ith and jth partials on the tangent space. Then yeah, so that G matrix should be symmetric and positive definite. And here on statistical models, which are already is quite similar to smooth manifolds, at least manifolds there now. So there we are getting something which is a function of theta. So okay, again, the information matrix is a function of theta, right? So I theta is the information matrix, and ij theta is the ijth element of the information matrix at the point theta. So this is quite good. And as we can guess, this will be very crucial while defining the Riemannian metric. Now, how to calculate this capital Ij? We already gave the formula, but sometimes it's useful to, there are many equivalent formulations of this Fisher information number and matrix. And we will use this following equivalent formulation, that the ijth element can be calculated as negative of the expectation of the Hessian of the log vector. Okay. Okay, so let's look at two examples, basically three. So I don't really should be doing this example now because I haven't defined the Fisher-Rao metric yet, but okay. So let's start with the exponential distribution, the simplest one, I guess. So p theta x is theta e power minus theta x. So now when you differentiate with respect to theta, twice. So here there is only one parameter, right? So it's just normal differentiation. So it's just minus 1 by theta squared. And therefore, now the matrix is just one element matrix and it's 1 by theta squared. Okay, so very, very simple. This is the Fisher information number, and also the Fisher information matrix is 1 by 1 matrix, 1 by theta squared. And now if we want to, so now we have a manifold. In manifold, we can't really find distance between 2 points. Okay, but we haven't defined anything else but a manifold yet. So we have no right to speak about length of a curve, which I have written here. Okay. But anyway, what we can do is we'll see. So suppose we have defined the Riemannian metric G on this statistical model, then how will the curve length be defined? It will be defined, suppose it's joining theta 0 to theta 1, it will be defined 0 to 1 square root of G on theta. Of course, you will take the norm of the derivative of the curve, right? So yeah, so as I said, so this curve length formula is also given before. Okay. And now what I'm trying to say is, what if this G11 is defined as 1 by theta square? It's not yet, but I'm saying what if it's defined in that way? If it is defined in that way, then the length, the curve length becomes integral 0 to 1 theta prime theta dot t by theta t mod over all that dt, which is again mod of ln theta 1 by theta 0, that is ln theta 1 minus ln theta 0. Okay, so yeah, so this is basically the hyperbolic distance function on the one-dimensional statistical model. So this is when we define G11 as I11 1 by theta square. Okay, so we are trying to somehow motivate that this G and I should be made equal. Okay, and then we can do good stuff. Okay, so yeah. So now let's look at exponential family. We'll just calculate the ijth element of the information matrix. That will be helpful later. Of course, we'll not do like the geodesic calculations and all. Like even if the geodesics and all are very important, simple concept geometrically, the computations of geodesics and so on require solving differential equations. And even in case of statistical manifold, it's harder because we work with non-symmetric connections sometimes. Like not always harder also, but okay. But the thing is, yeah, so we'll not do the explicit calculations, but we'll see some of them to get us to get comfortable with this. Okay, so exponential family is defined in this way. I think everybody's comfortable with that. It's just exponential of some function of x, function of data, and then there will be theta, like all the parameters, and for each there is a function of data fix, and then minus some function of theta. Minus is just for the sake of calculations. And then we can represent the Fisher information matrix in terms of the functions fix and also in the terms of the function like psi, right? Like the function of the theta. We are using two equivalent formulations of the Fisher information matrix. And we very easily get that the ijth element can be written as covariance of fi and fj, and also the partial I partial j of the psi theta. Okay. And it's also worthy to note the role of convexity of the function psi in the positive definitions of gij. Yeah. But yeah, so we work with all these assumptions, underlying assumptions. Okay, we want them to be good, so we are working with all the good assumptions. And then we also have mixture family. So one thing, we motivated information geometry. So information geometry is just defined as the geometry using Fisher information matrix. Okay, so whatever we are doing now falls under the category of information geometry. However, when it started, the name was not information geometry. It was just named as a geometrical differential geometric approach in study of statistical inference. But later on, it was termed information geometry. But anyway, we'll see that even if we can't see the the deepest motivations of them, we can at least see that how we can interpret this mixture families and exponential families, why they're special. Like we have seen, like we treat exponential families specially, right? But why they're geometrically special, we'll see that today itself. And yeah, after some time, we can also understand why like there are certain geometric interpretations and maybe sometimes a better understanding of the usual statistical inference or whatever we do. Yeah. So the mixture families are just the probability families given in this manner. Px theta is the cx plus theta I fix. Okay, so and again we are using the summation formula. Okay, so this summation convention, there will be sum over all the theta i's, whatever. And then this ij is defined as the Fisher information, ijth element of the Fisher information matrix. Again, by the formulation, we get to be the integral over the sample space of fi fj by the distribution function px x theta. So these are some formulations. This will help us to calculate. And all the good distributions we know, most of many of them come from exponential family. So yeah, it will help. Okay, so now we are ready with the basic machinery. We know what parametric models are. We know that we can look at them as manifolds, even smooth manifolds. So we can see this. So these charts and all locally, they're very, because the probability distribution function remains the same. We are not changing the parameterization at each point. So suppose we are parameterizing normal mu sigma square as normal mu sigma square, like the way we write it, and the next one we are doing it in some different way, then that's not okay. So we are parameterizing in the same way, then this local chart transformation or translations won't be much difficult. So it will be a smooth manifold and so on. So yeah, so we got a manifold structure on the parametric models. And we also saw that there is something called Fisher information matrix, which has something to do with the information contained in a data and how it changes along different directions. And that information matrix has certain good properties, like it's symmetric and positive definite if the geometric regularity conditions hold, and so on. And we saw how to calculate it. Okay. So now we see what was so-called, as many referred as path-breaking paper of 1945 by our own C.R Rao. The paper was named Information on the Accuracy Attainable in the Estimation of Statistical Parameters, and it was published in Kolkata Mathematical Bulletin. And it had two very significant contributions to the field of statistics. And you can't really go without naming it. One should name it, even if it's completely not relevant to our topic. Is the Cramer-Rao lower bound. So it was also introduced in the same paper. I guess everybody knows about the Cramer-Rao lower bound. So it answers the fundamental questions like how good a statistical estimator can be, or is there a fundamental limit while estimating statistical parameters. And the next one, which is more relevant here and which is also very important in the subsequent studies of statistics and other related branches, that is a Rao-Fisher distance, or the introduction of the Rao-Fisher geometry, where he first introduced a differential geometric approach on statistical models, giving them the nature of statistical manifolds. And this gave birth to what is now called information geometry. Okay. Okay. So let's see what the idea was. Okay. The idea was he tried to define a quadratic differential form. Okay. So he tried to see, if you are moving from a particular theta, so a point in a statistical manifold is what? Is a probability distribution, right? Is a density. Yeah. So, and it is signified, it is parameterized by theta. So each point is parameterized by theta, and which actually signifies a probability distribution function. So now, if we move along, move a small distance, then what is the error, the kind of the differential form? Okay, so there is no easier way to say it, but okay. Anyway, so this is just, again, using the summation convention. It is just, he's saying that if you go along the theta I direction and the theta j direction, then you approximate this as the ij, you take this as the coefficient, the ijth element of the information matrix, and then you take the respective distance you covered in the i direction, the j direction. Okay, and in terms of linear algebra, it's just delta theta, del theta, like the change in theta, from where you are going to where, and transpose of that, and then you have the information matrix I theta, and then again you have the del theta. So this is the change, this is the coordinate form. This is how we want to measure the loss, or yeah. So now how does Rao define distance? He defines distance between two distribution, probability distribution p theta 1x and p theta 2x. These two are again points, two different points on the statistical model, which is a manifold now. Okay, and now how they're defining the distance? They're taking smooth curves, again admissible curves from theta 1 to theta 2, and they know how the like small element lengths look like, and they're now integrating over them to get the whole distance of the curve. So he is basically doing this. Okay. So now, from knowing the geometric, differential geometric and Riemannian geometric framework, what he basically did in his paper was, without mentioning this, was the geometric modeling as GP partial I partial J is equal to the ijth entry of the Fisher information matrix. This is the fundamental idea of the Fisher-Rao geometry and any form of informational geometric modeling. Okay, we are setting the coefficients of the Riemannian metric as the ijth, like the entries of the Fisher information matrix. Okay. Okay. So with this brilliant modeling, so why this is brilliant? Before that, how do we compute Fisher-Rao distance? So he introduced the Fisher-Rao distance. One more thing, like this is not the only statistical distance. Okay, like even before introduction of Fisher-Rao distance, there were other distance. I think at least one was the Mahalanobis distance, d square, which is very famous d square statistic, and everybody again is comfortable with that. But yeah, so computing Fisher-Rao distance is a little bit difficult. However, it's very like it applies to wider range than any other distance function defined before. But it's difficult because again it requires you computing the geodesics. So to again, to find length of a length in a Riemannian manifold, you need to calculate the geodesic connecting the point theta 1 and theta 2. And after you get the geodesic, you just integrate it. But to solve the geodesic, as I said quite a few times before, you need to solve the ordinary differential equation, which is given in terms of this Riemannian matrix, GEIs and the coefficients and some partial derivatives and the Christoffel symbols of first and second kind. Okay, the first kind Christoffel symbols are defined like this. So there is no reason of breaking your head into all this. Okay, but yeah, so let's just move on. And the important idea here is what Rao did is he modeled the statistical model, the manifold, defining Riemannian metric in some way by using the ijth entry of the Fisher information matrix. And essentially, in his way, he defined this quadratic differential form. Okay. Okay. So now, why is this a good choice?
So there is a chat. So there is a question, if you can look at it.
Sure.
Oh, I see. Anupam has already answered this, but still.
Yeah, so the positive definiteness is ensured by the linear independence of the partial derivatives. Should I go back to it, or is it okay?
Yeah, it would be nice if you can go back to it once.
Yeah, sure. Yeah, so this is the place where we proved the. So for any Fisher information matrix, it will be symmetric and positive semi-definite. That is from the same proof. So till here, it's all same. Okay. But from here, if we, yeah, so if we need to prove that it is positive, strictly positive definite, then we need to show that it's zero only if the vector v is zero, like all the components are zero. And that is coming from the linear independence assumption on the partial thetas.
Okay, so okay. Yeah, fine. Thank you.
Yeah, so basically so this is the idea, and this is how we compute Fisher-Rao distance, which is not always very straightforward. But needless to say, it's a great idea. And why it's a great idea? So these are the reasons. So firstly, and this is a Riemannian metric. Why is it a Riemannian metric? Because by the definition of Riemannian metric, it should satisfy the condition that it's symmetric, positive, definite, right? By linear form. And it is the way we are defining it now, right? And also it's smooth and non-transition. We have to check the conditions, but yeah, it satisfies the condition for the most regular, under-regular assumptions and so on. And the second thing is that there are two very important invariance and covariance properties of this, like defining Riemannian metric by using Fisher information. So this Fisher information matrix is invariant under the reparametrization of the sample space. Okay, I think so. The proofs of them are not very difficult. Okay, so they just require some chain rules and all. But yeah, so but due to lack of time, I'm not able to cover all the proofs here. But yeah, so the proofs are not always difficult. Okay, the second one also, the proof is not very difficult, saying that the Fisher information matrix is covariant under reparametrization of the parameter space theta. So covariance mean it's not exactly invariant, but it is invariant in the sense of a tensor, from a sense of a covariant tensor. Okay. So this Riemannian metrics are basically tensors. Like you can think them as tensors. Yeah. So now, and these are not just the two important things. So these are saying that, okay, so these are invariant properties which we need while we are not just doing geometry here, right? We also need some statistical knowledge and some statistical idea in it, because these are, after all, statistical models. The points are not just any other point. The points are probability distributions. So they should be invariant under the reparametrization of sample space. They are. They should be covariant under the reparametrizations of the parameter space. They are. And also it's proved in, I think it's a paper like in 1990s or something like that. A Russian mathematician Ken Stov, I don't know if the pronunciation is correct, but he proved in a very difficult paper that it's basically unique. Like the only way to define a Riemannian metric on statistical models, which is invariant and covariant, like satisfying the previous two properties, is by using with some scalar, scalar factors will be same as the metric we get by using the Fisher information matrix. Okay, so this is something he proved long later after Rao's like Fisher-Rao information metric, like 20 years later maybe. Anyway, and to prove that, you need to go into abstract statistical manifolds and so on, which are again advanced topics. Anyway, and so the last and the most important thing is that it's a very intuitive informational modeling. By that, what I mean is, so this is a theorem about, again, it's a property of the Fisher information matrix. But what it says is, suppose you are, when we do statistical problems, what we do is we try to, from some given data, we try to infer about parameters, right? Modeling that the data is coming from a particular distribution and parametric distribution in this case. So what we are saying, what the theorem says is, suppose I theta be the Fisher information matrix of a statistical model S equal to P, X and theta. And suppose we take an induced model. By that, what I mean is you take a function of the data, let's say, okay, and then condition with respect to that function of the data. So that's the induced model, right? Because from the bigger model S, you can get the smaller model SF. So SF is the induced model. From Px theta, we're getting Q y theta, where y is just some transform function of X. You can think like that. Yeah, condition of that. So it says that the information matrix IF theta, which is on the induced model, will be less than equal to I theta, in sense that how we define greater than equal to or less than equal to in matrix is in the sense that the difference between them is positive semi-definite. Okay, so this del I theta, which is defined as the induced model Fisher information matrix minus the I theta. No, I think it should be the opposite. Sorry for that. I think it should be I theta minus IF theta. But whatever it is, I hope it's clear. It should be positive semi-definite. And then we say that it's greater than equal to. And the theorem says it will be. If you take any induced model, the information matrix will be strictly less, like will be lesser than. And the equality will hold if and only if F is a sufficient statistic for S. For those who are not comfortable with sufficient statistic, it's just a, like when you take a function of the data, but you don't lose any information, the information you need to estimate the parameter. So you have all the information you need to estimate the parameter, but you take a function of the data, not taking the complete data. Okay. So the induced model contains the same information as the bigger model. So that's exactly the case. So it's saying that our intuitive idea like holds, like is compatible with this definition and so on. Okay. So these are few, reasons why this modeling is really interesting, and it's a great idea to model statistical manifolds in this way. But as I said before, these are not the only statistical distances. Just to give you some idea of it, for example, another very famous statistical distance, Mohanobis distance. So the thing is, so this is something I should mention, I think. In this particular study where we are studying Riemannian geometric perspective of statistical manifolds. So as we are doing it on statistical models, which doesn't have any inherent geometric structure in that way, so we can do it in a number of ways, right? And there is no correct way and there is no wrong way. You can like our modeling is sort of, it's in some book refers to it as informative geometric modeling. So our geometry is like motivated by how the information of the information is distributed along the manifold or something like that, right? But yeah, so there are other distances too, which sometimes, so Mohan's distance was introduced by, like, he was trying to explain some anthropological data and some cluster analysis, something like that. Okay, so then so this is the fundamental question to ask, right? And it was asked even before Rao introduced the Fisher-Rao geometry, that how far apart two distributions are, or suppose there is a point and there is a distribution, what is the distance between that point and that distribution? And Mohan's distance answers that, but it's not the best distance. Okay, so the definition is just this, that suppose you take normal mu sigma, and let's say, yeah, so what is, yeah, so P and Q are taken into account. So you take the mean is P and Q, then the distance is P minus Q transpose M and P minus Q. Okay, and when M is some positive definite matrix. If you say M is, when M is identity, then it's just the Euclidean distance, right? Okay. There is also another sort of distance with Bhattacharya distance, and I don't know why all like Indian statisticians were so much involved with defining distances, and especially, of course, when I talk about Indian statisticians, they are always some associated with ISI. I think that's not very wrong to say. Anyway, so Bhattacharya distance is defined as distance between two probability distributions indexed by parameters θ1 θ2, defined as the following. But unfortunately, this Bhattacharya distance is not a metric. Okay, so like it's not yeah, so it's not a metric, but mononomial distance is a metric, I think. Yeah, but I think you can convert Bhattacharya distance in some way to get a metric, some Wilbur matrix or some metric or something it's called. So you can get it, but yeah, so these are just to give some two different notions of statistical distances. So as you can understand, these might be easy to compute. At least the mononomial distance is quite easy to compute rather than doing it in the Fisher-Rao geometry sense or the Riemannian geodesic sense. But the problem here is, see, we are only defining the distance assuming that the variance is constant, right? But so that is basically, suppose you are doing on the space of normal mu sigma square, you are just able to define distance on the one parameter subfamilies of that. That's not nice, right? But when we do Fisher-Rao geometry, we are able to define distance on any kind of subfamily and even the larger family. Okay, so that was all about Fisher-Rao geometry. Let me see what is the time. It's 4. Okay, so I said okay. Okay, so let us just quickly go through the alpha connections. So till now, what we did is, again to summarize, we saw the definition of parametric models, and then we imposed some geometric regularity conditions, which made the parametric model something like a manifold. And then C.R. Rao in his paper introduced the use of Fisher information matrix to define the Riemannian metric by defining Gij equal to Iij. That is basically what we're doing. You're not doing the I and j basis elements, partials. You're defining them as the ijth entry of the Fisher information matrix at a particular theta. So yeah, so now you have a full-phase Riemannian model. So you have to talk about alpha connections now in order to talk about geodesics and so on. So okay, so now as before also we talked about geodesics. So geodesics will depend on the connection you use, okay? But if no connection is mentioned, then we assume that the connection is the Riemannian connection or the Levi-Civita connection, the compatible and the symmetric connection. And we find the distance by finding the geodesic in that with respect to that particular connection. Okay. But so here is a very important, a very interesting study on statistical manifolds. So what are statistical manifolds now? I'm just like using the name, but I haven't defined it. So you can just think the statistical models after some assumptions, they are something like manifolds. So we call them statistical manifolds. And we give them the Fisher-Rao geometry. And now we want to give them some alpha connections too. And the thing is, the main direction of study nowadays in information geometry is the alpha connections and the alpha connections and the dual connections. Okay, so these are a very unique and a very interesting properties of statistical manifolds. Okay, so in statistical manifolds, we are not only concerned about the Levi-Civita connection, we are we are concerned about a large class of connections called the alpha connections. Okay, and we define the alpha connections like this. Okay, and this is just an expression with partials of the distribution and something with respect to alpha. Alpha is a real number, and expectation, right? So these are again the Christoffel symbol of the first kind, and we start with defining the connection locally because that's easier to do. So we locally define the Christoffel symbols of first kind, and then from there we go to the connection, and we call it the alpha connection if we define it in this way. Okay, so for each alpha real number we define a connection on statistical manifolds called the alpha connections. Okay. So here are a few properties. First is alpha connections are symmetric or torsion free. So that's first, and that's a very nice property to have. And the second one gives us a relationship between the alpha connection and beta connection in a very nice way. Okay, so these all have geometric interpretations. If I had time, I could have maybe spoke a little about this, but anyway. And then the most important thing is the zero connection, like the nabla zero. So we denote them as nabla alpha, the alpha connection. So the zeroth connection is the Levi-Civita connection with respect to the Fisher metric. So Fisher metric is a metric we defined using the Fisher information on statistical manifolds. So there is a unique connection which is Levi-Civita connection with respect to that metric, right? And that connection in this case is the zeroth connection, nabla zero. Okay. And the nabla alpha can be defined in terms of nabla 1 and nabla minus 1 in this way, in this very simple and elegant way. Okay. Yeah, so now these two are very important results and signifying the geometry and the speciality of exponential families. So exponential families are nabla 1 flat. If we remember, so should I go back to flatness of manifolds? Let me just go back once. So we say a Riemannian manifold to be flat with respect to a particular affine connection if the Christoffel symbols for that affine connection locally are all zero. Okay. And there are other equivalent this formulations also, but yeah. So we call them flat with respect to a particular connection. Okay. So now the result says that exponential families are flat with respect to the one affine coordinate system, like with respect to the nabla 1 connection. Okay, so exponential family is nabla 1 flat, and mixture families are nabla minus 1 flat. Okay, so these are very two important results. And like the natural parameters of the exponential families form a one affine coordinate system. If we remember, then to be nabla 1 flat, we need to have a nabla 1 affine coordinate system. This is called one affine coordinate system. And for mixture family, the natural parameters form a minus 1 affine coordinate system. And we sometimes call this nabla 1 connection to be exponential connection because it's flat with respect to the exponential family is flat with respect to nabla 1 connection. So we sometimes just call the exponential family is flat with respect to the exponential connection. So there are these two important connections. So the exponential connection and the mixture connection. So those are basically the nabla 1 and the nabla minus 1 connections. And as we can see, the nabla alpha, the general alpha connection can be written in terms of nabla 1 and nabla minus 1, the exponential connection and the mixture connection. E connection and M connection, rather, like these are also two heavily used notation.
What's the mixture family?
The mixture family, okay, so I define mixture family. I will just go back to there once. It's just like without the exponential part of the exponential, kind of. Yeah. So defined like this: Cx plus theta I phi x, and there is a summation over the theta i's, right? Yeah. Is it fine?
Yeah. Thanks.
Yeah. Okay. So yeah, so these are the two very important families, right? And now now there is another very important part. So, and this is now a study of mathematicians too, like the Riemannian geometers. And the concept of duality in connections and dual connections came from basically studying statistical manifolds and Riemannian manifolds. So it's not just we are taking mathematical theories and implementing them on statistics. It's also the other way around, at least to some extent. Okay, so what are dual connections? In an abstract Riemannian manifold MG, say nabla and nabla star are two affine connections. Then if they satisfy this for all vector fields, smooth vector fields x, y, z, then we call nabla and nabla star to be duals with respect to each other. Okay, and dual connections of each other. We additionally call G nabla lambda star a dualistic structure on S. Okay, and we call M to be dually flat if it is flat for both. It's both nabla flat and nabla star flat. Okay, and there are very interesting properties of dually flat manifolds. That's basically the study. Okay, and we'll see like so we'll go to the next theorem, but before that, so dually flat manifolds and the study of divergence. So what are divergence? We also talked about like divergence and distances. So like divergence can be thought of like a general notion of distance, which doesn't need to satisfy anything like symmetric property or the triangle inequality, but it should be positive definite. And there are some Pythagorean relation between divergence or something like that. So yeah, so those are, general forms of distance that one can define on dually flat and dualistic structures and manifolds and so on. And those are like the current nature of study on information geometry. Okay, so this is the definition of a dualistic structure on a manifold, and we call the manifold to be dually flat if it's both nabla flat and nabla star flat. That is flat with respect to both nabla and its dual. Okay, and the key result on statistical manifolds or statistical models with Fisher-Rao geometry is that, okay, and now when you talk about flat or something, so flat with respect to a particular connection, we should have, we're assuming a metric, okay, a Riemannian metric. Without a Riemannian metric, we can't talk about connections or anything. Okay, so yeah, you can define a Riemannian metric without even defining a connection. That's, of course, we are going in that direction. But while we are talking about connection, geodesics, and any kind of structure on connections, we have to assume because the connection is an interdependent structure with the metric. Okay. Okay. So now this on statistical manifolds with Fisher-Rao geometry, we have that it is nabla alpha flat if and only if it is nabla minus alpha flat. Okay. So I will try to write something here, but my pen is not working for quite some time. Yeah, it's working. Good. Yeah, so this actually it's true for it says that any dual connection will have the constant curvature. Okay, so like this is a theorem on Riemannian manifolds. If this has connection, this has curvature tensor, let's say plus r, then the dual of it, if there exists a dual, will have minus r. Okay, and so that is the thing. And if it's flat, that means the curvature tensor is 0. So it's always true that if there is a connection which has curvature tensor 0, which is flat, then the dual connection will also be flat. But there is a thing here. The problem here is it might not be symmetric. It might not be torsion free. So we can't really do geometry nicely if it is not symmetric. Okay. But for statistical manifolds, all the connections are symmetric, right? That is also a property we saw earlier. Yeah. So all the alpha connections are symmetric. So for statistical models, we can say that nabla alpha is flat if and only if nabla minus alpha is flat. And this is true for any alpha. Okay. So now we knew that exponentials are nabla 1 flat and mixtures are nabla minus 1 flat. So basically exponential and mixture families are dually flat. Okay. With respect to the dualistic structure, G nabla 1, nabla minus 1. Okay. And then like to just give a glimpse of natural, like the current study and the field of study of information geometry and mathematical structure of it, we define abstract statistical manifolds. We start with a statistical structure, which is a triple MGC, where G is a 3 covariant totally symmetric tensor. Okay, this is called the skewness tensor. The skewness tensor are introduced in different ways on a Riemannian manifolds. This is a particular way. Okay. And then from a statistical structure, one can really construct a statistical manifold, which is just it has a manifold M, a Riemannian metric G, and there are two dual connections, like a pair of dual connections, nabla and lambda star. So those are basically the nabla 1 and lambda minus 1. So this is basically abstract formulation of statistical manifolds. So now, like as I said, proving the theorem that there is only one possible, the Chen-Stoff theorem. So all this proving different results, and on much more abstract plane, one need to use statistical manifolds and stuff like that. And defining, there are different kinds of divergence. Divergence is one defined on statistical manifolds. And also there is a key concept in information geometry now, what is called entropy. So they define entropy for a particular theta, so on a parameter, so entropy of a distribution, and try to find the distribution with the maximum entropy. Okay. And so those studies are like heavily related with all these abstractions and mathematical constructions. So let us just end this talk with some concluding remarks. The study that began with Rao's paper 1945, which introduced the Fisher-Rao geometry, it was first introduced to study the statistical inference properties, as the tangent space is a space which gives the linear approximations, right? It's a linear space. Yeah, and so studying asymptotic statistical inference on the basis of the tangent space is one way to look at it. And C.R. Rao, Amari, and other people worked along this direction. So this is called the Fisher-Rao Riemannian geometry. A completely different direction is this Amari's dual connection information geometry direction, which goes on defining abstract Riemannian and geometric notions on statistical manifolds and so on. There are applications on different other branches, including optimal transport geometry, quantum information geometry. So so it's very much intersecting with the information theory, because if not anything, it can provide us useful and very intuitive thinking pattern and arguments for information geometric results. And these are few references I used. The first one is the path breaking paper, and this paper was also included in a book called Breakthroughs in Statistics. There is a volume 1 and volume 2. So, and the sad part is when the paper was actually published, it was there was not much of a discussion about the paper, because the heavy use of differential geometry and mathematics. So C.R. Rao was a great mathematician, but at that point of time, most of the statisticians were not aware of all these differential geometric mathematical formulations. But later on, it got interest from different areas of the world, and there were studies and monographs dedicated to particular study of information geometry. And I think the most standard text is The Methods of Information Geometry by S. Amari and Nagaoka. It's this one. Yeah. Yeah. So I think that's it for today. If there are any questions, and
so thank you very much, Soham. If anybody wants to ask any question to Soham about this talk or any other related material to the things he discussed today, feel free to ask.
All right, I'll stop the recording.